So to recap, error term is associated with the difference between the observed data, which is your sample data, versus the population data, whereas the residual is associated with the observed data, which is your sample data, versus the predicted data, which is the estimated regression equation. Hope this clarifies. Error of the data set is a difference between the observed values and the true or unobserved values. The true or unobserved values is nothing but your population data, right, because it is unobserved. A residual is a difference between the observed value, which is basically sample, and the predicted values by the model, which is here called as estimated regression equation. So with this idea, let us go for what is called as residual analysis. So that means what? Initially I had taken 4 assumptions about the error term, which is related to the population, but I cannot straight away check the population error assumptions, and hence what I do, I check for the sample data, which is I get a residual from the actual value, that is a sample data versus the predicted value. So if the sample data versus predicted value satisfies the error assumption, then automatically I can say that error assumptions are validated. Let us go for one by one. So first one is the normality distribution of residuals. Just to recall, what is the assumptions? Error terms are independent with a mean 0 and constant variance and normally distributed, right. So this is a normal distribution of the error terms assumptions. So error is replaced here with the residuals. So if the residuals are normally distributed, it is understood the errors are also normally distributed. So how do I check for normality of the residuals? So this is how I check for. There is something called as PP plot, right, probability plot we call it as. What does it do? Compares the cumulative distribution function of two probability distribution against each other, right. So ideally we want a normal distribution, whether that normal distribution and whatever I have with respect to the residual, whether it superimposes or not. If it superimposes, then ideally it follows a normal distribution, right. So residual and normal distribution, the cumulative distributions are compared. So it looks something like this, right. So if you look at it, this is a theoretical probability on your x axis, this is a sample probability. The diagonal line represents the ideal value if your data set is following a normal distribution. These dotted lines are basically your residuals, right. So if it is in and around the line, then we can safely assume that it is following a normal distribution. If it is very much away from the line, the dots are very much away from the line, then obviously there is a concern that it may not follow a normal distribution. So in PP plot, diagonal line represents the cumulative distribution of normal distribution, and whereas dots in this case represents the cumulative distribution of residuals. What is the inference? If the dots are very close to the diagonal line, we can conclude that residuals follow a normal distribution. If the residuals follow the normal distribution, automatically we can safely assume that error also follows a normal distribution. So the error assumptions of normality is satisfied here, that is only one, so which is good for us. Moving on. Second assumption is about constant variance, right. So that means the error is having a constant variance. So how do I check that? That is called as homoscedasticity. That is, if the residuals have a constant variance, obviously the error terms also will have a constant variance. So now we are checking. How do we check it? So we put a graph against standardized residual values versus standardized predicted values, right. So obviously we need to standardize it so that the scale part of it, usually the residual is less in value, whereas the predicted value might be more, right. Say for example, salary, in this case salary is equal to, depending upon the experience and the score, right. So if I take the sales, right, as a predicted value, sales value will always be more than the residual value. What is the residual value? The actual sales minus the predicted scales, right. So that might be less in value, since the scale will be completely different and then it will throw off in the graph. So we are standardizing both the residual values as well as the predicted values. So if I put a graph of standardized residuals versus predicted values, right. So standardization means actual value minus mean divided by the standard deviation. That's what we are calling it as a standardization. So if we put a graph of this, if I get a random pattern or a horizontal band, I can safely assume that it follows a constant variance assumption. That means it satisfies constant variance assumption, that is errors are having constant variance or uniform variance. That is good for us. If it follows a particular shape, right, so usually funnel shape, right, so something like this, let us say this is the graph I put and it follows a funnel shape, these are the residuals variance, right. If it, as we go along, if you see there is no linearity and the variance keeps on increasing, right. So if you follow something like this, then we call it this as heteroskedasticity, right. So this is explanation of heteroskedasticity, and this is not good for us. What is good for us? Something like this, right. So this is your random pattern. Horizontal band, what they call, so if you look at a particular standard deviation, let us say in this case minus 0.5 to 2.5, all the things are in between this, right. So it is between a horizontal band of minus standard deviation to plus standard deviation. To further understand, because this is one thing that sorry, one thing that keep on coming up in the standard question, right, whenever you say that you know multiple linear regression. So let us try to understand this, right. So let us take an example. This is your independent variable and this is your residual, right. So this is a simple graph saying that how residual and independent variable are related. So this is just a beginning, let us say. Now if I go for testing of homoskedasticity and heteroskedasticity, so B, if you look at it, residual versus your dependent independent value or the predicted value, right. So either way you can do it. So if you see it, it follows a random pattern and it is between a horizontal band, right. So in this case the residuals are not standardized, right. So if you look at it, the scale is moving beyond, so that is okay in this case, right. So it is between the, so this is good for us, follows a homoskedasticity. So this is between x and y, right. So x is your dependent variable and y is the independent variable. Basically it says there is a linear relationship, right. It is not related with anything. So in this case also it is a random pattern, right. So if I say graph A and graph B, essentially it says almost the same thing, right. So here you can see the horizontal band, here you see the random pattern. Either way we can say that the error is constant variance or uniform, right. So this is a simple representation that x and y are related, where x is your independent variable and y is your dependent variable. Now what is heteroskedasticity? This is heteroskedasticity, right. So x or y and then the residual, right, can be standardized or not. If it follows, these are all the residual value, right. So if I plot between the residual and x or y hat, that is your estimated value, it follows a funnel shape, right. So if you look at it, as we go along it increases, the variance increases, right. So this is not what we want. That means heteroskedasticity. Heteroskedasticity will affect the estimation, right. So beta coefficient estimation it will affect, standard error estimation it will affect, and since it affects both, obviously the model will not be valid for prediction, right. So it's an important thing that we need to remember. Homoskedasticity is a must if at all I want to implement the model or use the regression equation for prediction purpose. So far we have discussed about normality of assumptions and constant variance assumption. Moving on, we need to go for uncorrelated error terms. What is this uncorrelated error terms? That is, we have assumed that errors are independent of each other. So that means errors cannot be correlated. The one occurrence of one error will not either increase or decrease the occurrence of the other error, right. So in the sample you can assume to be, right. Now if they are correlated, then it is not a random error, right. So that is the idea behind it. So how to check whether they are correlated or not, that means errors are independent or not, we have something called as Durbin-Watson test. So before that, that phenomena is called as autocorrelation, right. So what is autocorrelation? Let us try to understand it, right. A variable which has no statistically significant relationship with the response variable may be accepted in the model due to presence of autocorrelation, right. So what is this autocorrelation, right. In this case the errors, if the occurrence of one error as influencing the occurrence of the other error, then these errors are correlated, which we call it as autocorrelation. So, autocorrelation is more relevant in terms of time series data, but in terms of error assumptions we need to check for it. How do we check for it without getting into technicality or formula part of it? We have something called as Durbin-Watson test. So, Durbin-Watson test gives you negative value and neutral value to positive value, right, and as a rule of thumb, right. So, if your Durbin-Watson statistics when you are testing for autocorrelation of error term using residual is close to 2, then it implies the absence of autocorrelation, which is what we want, right. So, this is the test that we need to carry on for checking whether the errors are independent and are not related to each other. So, pretty much that is it with respect to residual analysis, and one more check before we close on the model diagnostics that we need to take care is what is called as multicollinearity. What is multicollinearity? If the independent variables are correlated with each other, right. So far we have discussed about all things about error terms using residual analysis. Now one more phenomena also can affect the prediction of the regression model, which is called as multicollinearity. So what is multicollinearity? Let us find out. The term multicollinearity refers to correlation among the independent variables. If the independent variables are correlated among each other, then this will unnecessarily affect the prediction power. So put it otherwise, if the two variables are highly correlated, they are not giving me any different information, they are telling the same information, and hence I do not need two variables, only one variable will suffice. When the independent variables are highly correlated, say for example correlation is more than 0.7, it is not possible to determine the separate effect of particular independent variables on the dependent variable, and hence we need to drop one variable, otherwise it will account for more prediction power or less prediction power, and hence my prediction accuracy goes for a toss. Say for example in our example, salary is related to experience and the score, right. Let us say the score and experience are highly related. Now this is called as multicollinearity. So that means I do not need two variables here, experience and score separately, since they are highly correlated. Either the experience will explain what is the variation happening in the salary, which is your dependent variable, or the score will explain what is happening in a variation with respect to salary, and I do not need both variables to explain. That is the presence of multicollinearity. If you find the independent variables are highly correlated, what essentially we do is we run the regression using one variable at a time and try to estimate your R square, right, and then see which variable gives a better R square, and you keep that variable. Yes, the other variables can be dropped, but the condition is both of them should have a high correlation, which is greater than 0.7. That is your multicollinearity. How to check or which two variables has a multicollinearity? So this is the test that we use for checking the multicollinearity, right. So I will read out once again what is multicollinearity: the existence of high correlation between independent variables, right. So independent variables is called multicollinearity. We have got something called as variance inflation factor. So if two variables are highly correlated, how it gives? It gives a VAF value. How does the VAF value calculated? So essentially it runs a simple linear regression between the two variables, right. Here in this case let us say x1 and x2. So it forms a simple linear regression, and using this it calculates the R squared, and the VAF is calculated using 1 divided by 1 minus R squared. So here obviously you will get the value, and people have found that if the VAF value is greater than 4, then there is a suspicion that there is a presence of autocorrelation. That means those two independent variables might be related, and hence we need to try with one variable at a time and try to find what is the R square, right. So further investigation to assess the impact of multicollinearity. So remove the variables with VAF is equal greater than 4, right. If it is greater than 4, then it is not good, right. We need to avoid the multicollinearity. So you get the correlation matrix, right. So this is a correlation matrix, right. So, visual representation of correlation matrix. So, high density basically says that correlation is high. So, you can take a note of which are all the two variables which have a high correlation, and then see what is a VAF value. When you run through the SPSS or any other software, it gives a VAF value for particular independent variables. The VAF is greater than 4, then make a note of what are all the two variables, and then run the regression with only one variable at a time and see whether there is a improvement in R square. Right. So, that is a way to fix the multicollinearity. So, we come to the conclusion of all the things related to multiple linear regression. Hope you find it useful. Thank you very much.